Hey everybody, it's Dr. J, and today we're talking about valence bond theory. Let's talk chemistry. Lewis structures are a great theory overall to use, if you're doing something quick. However, it's so simple. It's too simple, a matter of fact. It doesn't give good number data. All right, so you're not ever going to get good data such as bond length or bond energy or actual angles. Okay, so because this is a simple way of basically determining your shape, of course, somebody came up with a new theory that's going to give you a little bit more data, and that is valence bond theory. So, valence bond theory is going to be using quantum mechanical models to understand chemical bonds now, right? So, a couple of different things we want to discuss before we jump into valence bond theory. Remember that valence electrons are always going to be in your atomic orbitals, your S, your P, your D, and your F orbitals. And when we think about chemical bonds, we understand that chemical bonds are coming together, which in fact basically involves overlapping half-filled orbitals. All right, so basically we understand, right, when we're bonding, when they're coming together for bonds, they're becoming more stable, right? That's because we're filling in those orbitals. Okay. Now, the result of this overlap of bonds, we call these hybridized atomic orbitals. All right. So this is kind of a blend or combination of those standard atomic orbitals that we mentioned before, S, P, D, and F. Okay. And based on this, we could determine a new geometry of those overlapping orbitals to figure out our shape of our molecule. So for example, right, if we're talking about H2S here, right, we know that hydrogen is a 1s1, and then sulfur, in this case, is going to be 3s2, 3p4, okay? So right now, all these examples are having a half-filled orbitals. When they come together, right, when they fill them in, right, this is where, when we add this hydrogen here and this hydrogen here, we're going to have our filled orbital, right? Once again, 8 valence electrons. Once it's filled, right, now we could determine the shape of our molecule. So that's going to look something like this. Over here, right, our bonds are forming between our S, in this case our 3p orbital, and our 1s orbital. So this overlapping is what we're talking about with the hybridized atomic orbitals here. So, right, what we find out is that this theory actually gives us a good bond angle. Predicted bond angle is around 90. The actual bond angle is 92, right? So this is more accurate than the Lewis or even VSEPR theory, which in this case, it would have predicted that it would have been 109.5. Okay, so this is what we're talking about, right? Each theory just gives us more details, and valence bond theory gives us more details. So hybridization is basically a math procedure in which the standard orbitals are going to be combined to form their new atomic orbitals. So basically the standard atomic orbitals are going to be added together, and those atomic orbitals are going to equal your new hybrid atomic orbitals. Okay, so you're never going to have a different amount of orbitals. Those things are always going to be equal to each other. Okay, so depending on, right, your combinational standard atomic orbitals, right, it's going to give you these new shapes and energies for your hybrid orbitals. Okay, so remember that a particular type of hybridization that will occur will give you your lowest overall energy, right? We all want to be stable. In this case, these bonds want to be stable. Okay, so if we look down here, right, these are our hybridized mixed orbitals. Okay, so once again, this is the overlapping of some of these. We got SP, SP2, SP3, SP3D, and SP3D2. Let's talk about these hybridization atomic orbitals. All right, so let's look at Sp3 hybridization. All right, so we're going to look at a sample example here, right? Methane, CH4. So methane, the bonding is only going to involve the valence electrons. In this case, between our 1s and hydrogen and our 2s, 2p, and our carbon here. So what we're going to see, right, if we look over here, how we're actually forming these Sp3 hybrid orbitals, is that carbon is actually going to be bound to 4 other atoms. Okay, in this case, it's going to hybridize the 2s and the 2p orbital. okay, to form these 4 new sp3 hybrid orbitals, right? So this is what we're talking about with it being conserved, right? In this case, it's between our 3 p orbitals and our 1 s orbital, right? Our unhybridized are just standard atomic orbitals, and they're going to combine to form our 4 new hybridized orbitals, right? So if you have 4, you're going to end up with 4. All right, you're not going to go from 4 to 5 or 4 to 6 or 4 to 3. It's going to say 4. So in this case, our first one is sp3 here, sp3 here, sp3 here, and sp3 here. All right, so they're all separate. But when we put them together, they look like this, right? In this case, having that bond angle of 109.5 when they're all together. And this is sp3 hybridization here. Now, taking that a step further, right, if we look at sp3 hybridization, we can see, right, our 2s and 2p coming together to form our new sp3 orbitals here. Okay. So, right, once again, 4, so it's the same stuff here, right? And then we got to remember, right, they're degenerate. What's that word mean? Degenerate? Basically, they're the same level, right? Same energy level. So they're the same energy levels because we mix both of these together here. So if we look at, for instance, once again, methane, right, those hydrogen atoms of methane can only use their 1s orbital. Okay, so when they use their 1s orbital, they're going to share those electrons and overlap with our sp3 orbital here. Okay, so now basically, right, this is what's happening with this hybridization, everyone. The carbon, once again, the carbon, let's go back here. The carbon is forming this new sp3 orbitals here, right? And when it comes to bonding, right, it's going to take those hydrogens and those 1s orbitals will be bound to that new sp3 orbitals, okay? Now, NH3 and H2O also use the sp3 hybridization, even though they have lone pairs, right? So in this case, NH3, here we go, lone pair here, but it's still a sp3 overall. Next, we have sp2 hybridization. Example is like ethylene, right? Ethylene here. So what's happening with sp2? Basically, we're taking the s orbital and 2 of our p orbitals. And what we're doing is taking these 3 orbitals, combining them together to form our new sp2 hybrid orbitals. Okay, so that's essentially it, right? sp2, and then it's it's telling you guys, it's telling you. S, we got 1s orbital, p, in this case we got p2, we're going to have two p orbitals, right? And that's essentially what sp2 hybridization orbitals are, right? 3 of those here. So once again with sp2, right, we took that 1s, and in this case 2 of our 2p orbitals, right? So in this case, when we go to look at it, we got our hybridization to where now we got those 3 orbitals, those 3 sp2 orbitals, but now we got 1 extra p orbital left over. Okay, so this is going to be left unchanged. In this case, it has a higher energy. Okay, now what does that mean? That means, let's talk about sigma and pi bonds. So sigma bonds, right, are going to be interacting with our atomic orbitals, pointing along our axis, combining our 2 bonding nuclei. Okay, so if we look over here, basically, right, they come together to form our sigma bond, overlapping of the orbitals. But notice how they're interacting, right? They're interacting like together in this way, right? Axes is hitting each other, right? They're interlocking in a way. Okay, overlap, sigma bond. Sigma bonds are very strong, right? Because of this interlocking that they have, right? They're sharing that between those 2. Now, the other bond is what we call pi bonds. Pi bonds are once again half full, but when they come together, right, it's a little bit different. In this case, they're going to be parallel to each other, and they're actually going to be perpendicular to their axis. Okay, so this is our pi bond. Now, our pi bonds are only going to happen when we have an unhybridized p orbital, in this case here. So essentially, here's a little shortcut, everybody. A single bond is going to give you a sigma bond. If you have a double bond, that means that you're going to have a sigma bond and one pi bond. Okay. And then a triple bond, that means that you have one sigma bond, but you have two pi bonds. And then this key is very key to understand that sigma bonds are going to be stronger than your actual pi bonds. So if we look at this even further, right, we got our carbon, which in this case is going to be sp2, right, as we mentioned before. And when it combines with hydrogen, right, we see the overlapping here, here, and here, interlocking. And then they are here, right? Once again, acids coming together, our sp2 over sp2. Now, if we break this down, right, and we talk about the pi bonds, because, right, in this case, the Lewis structure is telling me that, okay, if I see a pi bond, a double bond, I should expect to see one sigma bond and one pi bond. Well, when we come to draw these out, right, which you guys will have to do, all right, so in this case, we got our p orbitals here, right, in this case, our pi bonds. Our pi bonds are forming between our p orbitals, right, because, right, once again, we got this extra p orbital, right? It's unhybridized, right? So because we got this extra p, I expect to see a p, right, or a pi bond. So this is what we see here with our ethylene, right? With the overlapping of our sp2, right? We see our sigma bond form, right? Our sigma bond here, all right, the overlapping. But then we have our pi bond as well, being perpendicular, all right? So once again, because we have this double bond, we have one sigma bond, which is here, and then we're going to have one pi bond, which is here. All right, so this is the same thing, right? But this is just showing my sigma bond and my pi bond here, not showing everything else that's going on. Okay. But this is essentially it, everybody. This is hybridization, right? This is a lot more detail all in one. Now I'm quickly going to talk about bond rotation as a little quick interjection here before we get back to it. With bond rotation, basically, we're going to have orbitals that are going to form sigma bonds. All right, and we understand that they're like interlocking like this, right? So, because they're interlocking like this, the bond does not require any breaking of the interactions between our orbitals. So basically, right, because we have this interlocking, this single bond, the sigma bond, we can have rotation around. All right, so we can see rotation, and we see right here, right, the carbon is able to rotate around, right? So it's free rotation around this single bond. Now it's going to be different if you have some pi bonds going on here, right? So pi bonds aren't really going to be able to rotate, right? And that's because of this one right here, right? We see like a double bond in this case. It's going to be very hard to rotate this around, right? In this case, they're kind of like locked in their position, right? Because you can't do nothing with this big old pi bond in my way. This one, no pi bond, able to rotate. This one has a pi bond, so we're going to be restricted as far as how we're going to rotate our atoms together here. We're only going to mention this a little bit. We're not going to go too deep into this. This you kind of see this more in organic, but essentially, let's look at this point. Since the pi bond between the two carbon prohibits free rotation, these two molecules are distinctly different. So this is what I was talking about with the pi bond, right? Because we're not able to rotate, depending on where certain things are located, you're going to have a totally different molecule. So for instance, and this is touching organic a little bit. You guys aren't going to get into organic, but you're going to be exposed now. Cis 1,2 dichloroethane, right? So dichloroethane is letting me know I'm going to have two chlorines, right, bound to my double bond here, right? So cis is letting me know that my hydrogens are on this side, one side of each other. Trans is letting me know that they're on different sides of each other. That's essentially it. But based on this, right, because they're a pi bond, they're going to be stuck in this arrangement. Because they're stuck in this arrangement, right, it's always going to be cis or trans. All right, that's essentially what that's saying there. Okay. But that's bond rotation. Let's go back, right, to valence bond theory. So sp hybridization, basically, right, this is when, in this case, we're taking one s orbital and one p orbital, but we have two unhybridized p orbitals left over. So we see our two sp orbitals being degenerate on the same level. In this case, we're going to have that 180 degrees apart, but we will have two unhybridized p orbitals. So what exactly does that mean? Well, with sp, you're probably going to have a triple bond. Okay, so we can see it here as I broke it down up here. But let's look at an example, right? Lewis structure. Let's say we got a triple bond carbon, and with a triple bond, as I mentioned before, triple bonds, you're going to expect to see one sigma bond and two pi bonds, right? That's just a quick way and easy way to know these things, right? So because I'm going to expect to see one sigma bond and two triple bonds, when it comes to drawing out these valence bond models, then that means, right, that, well, my carbon is going to have a hybridization, as we mentioned, of sp. So sp is going to be linear right here when we combine them together, a 180 degrees angle. So we can see our carbon has 180, carbon has 180, and they're going to form this sigma bond between the two, right? A sigma bond between my sp and my sp, which we know we're going to have one sigma bond. But we're also going to have two pi bonds, right? Two pi bonds. Now, why do we have two pi bonds? Because we have these two unhybridized p orbitals. So it's taking into account the two pi bonds that we're going to see here. So we're going to see 1 and 2 here, right? So we're going to have our pi bonds between our unhybridized orbitals up here, all right? And this is what we see right here. And of course, we got our hydrogens being bound, their s orbitals, to our now hybridized sp orbitals. All right, and once again, this is sigma bound. So we also have sp3 hybridization. So this is atoms with 5 electron groups, and because in this case it's going to have 5 electron groups, they're going to be using their d orbitals from the valence electron shell, specifically their empty d orbitals. Now, you're only going to have sp3 hybridization with third row elements and down. All right, so anything third row and below, and that's due to, right, you guys remember Lewis structures when we talked about expanded octets? Same thing here, right? And in this case, that's going to be trigonal bipyramidal electron geometry, which we mentioned with VSPER. So when we're talking about sp3 hybridization, it's literally as it sounds, guys. It's s orbital, there's 3 p's, and then there's 1 d, right? So we're taking all of these, putting them all at the same energy level. So now we got our hybridization atomic orbitals. We got 5 of those, right? Because we took 5 of these. And then we're going to have 4 unhybridized d orbitals left over. So essentially, it's going to look like this, everybody, for our valence bond model. So this is our Lewis structure. And then what we're going to see, right, is that we can just basically translate this Lewis structure to this with our 5 electron groups. Looking very similar to trigonal bipyramidal. So what we're going to find out, everybody, is that you kind of, if you know Lewis structures and VSEPR theory, this is going to make it simple to determine some of these shapes for your valence bond model. So in this case, we're going to see sigma bonds between them all. And then lastly, we got sp3 hybridization. In this case, taking a 6, 1 from our S, 3 from our P, 2 from our D. In this case, it got to be third row and down because we're using these d orbitals now. In this case, it's going to look like octahedral, right? So we're going to have 6 of our sp3 hybrid orbitals, and then we got our 3 unhybridized d orbitals left over. And then we got our valence bond model looking like this here. Very similar to our octahedral electron geometry.